Okay, so let's get started. So, so transformation from probability to odds is a monotonic transformation. Okay, in other words, when probability increases, odds increases too, and vice versa. Okay, here, okay, we especially draw a figure to show that fact. I mean, one thing to be careful is that, okay, probability obviously is in the range of 0 and 1, but the odds, okay, is in the range of 0 and infinite. Okay, so because it's a ratio of two positive numbers, okay, but you know, and those two numbers are obviously, you know, one is like theta, one is 1 minus theta. Okay, you can imagine, okay, such a combination, okay, the smallest can only be 0, and where theta is 0, okay, and when theta is close to 1, okay, you get like infinite, okay, so and because it's like in this range, when you know use the log on this range, you get negative infinite to positive infinite, right? So I mean, you know, here it goes. Okay, this blue line shows the log odd. Okay, log odd. Okay, so it's you know, and the sigmoid. This one shows the sigmoid. Okay. Okay. I think, sorry, the blue line shows the odd. So it's from 0 to infinite. And this one, this orange one shows log odd, because log odd is I mean, you apply the logistic function to it, so it's like a sigmoid. It's a S shape. So you can see that, you know, no matter which point you are talking about, they increase, you know, together. Okay, even though the amount of increase is not linear. Okay, it's not proportional, but I mean they increase, you know, both increase. I mean, you know, being together. And the value of the coefficient provided by summary in the log odd scale, okay, log odd scale. By the way, like if you remember, like you know, because we in MCMC chapter, we talk about, we already cover the effective sample size. We already talked about the MC error, okay. So now, okay, you know the mean, you know the standard deviation, you know the MC error, you know the the HPD 3% to 97%. This basically indicate like a 94% HPD the range of the 94% HPD and the effective sample size. The only thing we haven't covered is this R hat. Unfortunately, we probably don't have a chance to cover that this semester. Okay, so once you try to output this the alpha, beta 0, beta 1, all the variables. I mean the statistic of all these variables. And it looks like this, but these are, you know, in log R scale. Okay. So one way of understanding the model is to change parameters and see what happens. So in the following block of code, so we are computing log odds in favor of versicolor as log odd versicolor. Okay, I mean, which is like this one. Okay, so and then the probability of versicolor with the log logistic function. Okay, So we repeat the computation by fixing x2 and increasing x1 by 1. So if you try to do that, okay, by using this piece of code, what you are going to get is that, okay, the increase in log R, okay, is about 4.66. Okay, if you run this piece of code, okay, and this is, close to the value of beta 0. Okay, the beta 0 is 4.65. So which tells you that, okay, if you increase the, in log R, okay, it's going to result in like, the increase of 1 beta 0 value. I mean, well, it's not exactly the beta 0, okay, but it's a number very close to beta 0. The reason because, they are different is just because of like, we are talking about this, it's statistically, okay, they are very close. It's just because like, we're talking about like a posterior, it's a distribution. So after all, it has something to do with like sampling. So sometimes it's a little bit slightly different, but the difference is almost negligible. Okay, negligible. Okay, so so this is in line with our previous finding. The encodes the increase in log R, unit by unit increase of the x variable. So yeah, so the increase is in the probability. Okay, once you apply the log to it. Okay, it's 0.70. Okay, so increase of probability is huge. Okay, because remember the probability is between 0 to 1. So just increase like x1 by 1. The probability increased by 0.7. Okay, that's because it's close to. It actually is close to. Because it's close to the middle, so that's why like it increased very quickly. Okay. So one thing also that we also need to know, be careful is that, okay, remember like in a linear regression model chapter, we talk about this, when two features are highly correlated, then it's going to create some problem. I'm not sure if you still remember, okay, because it was like, we talked about that, and then we went to talk about MCMC, now we are talking about this chapter, so maybe some of the content in the linear regression model has been, you guys have have already forgotten, but you can check out like the handout, quickly and to refresh your memory, okay? But anyway, okay, so if variables are highly correlated, yes, it will create some problems. Especially like they are, you will find it difficult to restrict the posterior, okay? The resulting posterior. So it's because like these variables, because they are highly correlated, they are affecting each other. You can even like consider them to be identical, okay? And we talk about this like in a linear regression model, okay? You can check. Again, check out that part. By yourself, okay? Because we are running out of time. I really want to cover, some additional material anyway. So the same phenomenon, okay, will occur, okay, in the logistic regression model, okay? So, correlated data has less power to restrict the model, Okay, that is why, as I say, the resulting posterior, okay, is going to be much wider. Okay, when there is no overlap between classes, given the linear combination of variables in our model. Okay, so using the iris data set, okay, we can try running model 1. This time using the petal width and the petal length variable. Okay, the reason we use the petal width and the petal length variable is because, okay, you will find that the beta coefficients are broader, much wider than before, and also the 94% HPD, this band in the figure is much wider. First, let me show you the petal width and the petal length. Okay, where is it? Here. Petal length and petal length and petal width, right? So you can see they are highly correlated. Okay, they are highly correlated. And originally, okay, we use sepal length and sepal width. Okay, so sepal length and sepal width, you can see that, okay, I mean, they may be slightly correlated, but the figure, suggests that, these two values are not that highly correlated, right? Compared with like petal width and petal length. This one is obviously, it's much closer to a line, right? It doesn't matter which species you are talking about. Okay, I mean, all these points are almost fall on a line. Okay, so obviously the petal length and petal width are very highly correlated compared with sepal width and sepal length. So this one, okay, you will find this band, okay, if you use if you change to two highly correlated features, you will find this band becomes much wider. Okay, so yeah, this is because if you check out the petal width and petal length, okay, the correlation is 0.98. That's very, very high, right? The correlation is very close to 1, right? But the sepal length and sepal width is only 0.21, okay? Well, it's correlated a little bit, but not much, right? Compared with that 0.98. So this is like the issue, okay? So figure on the right, I mean, it's a heat map. This heat map basically shows like the correlation between like different features. Here we only output the absolute value of the correlation. Correlation can range from -1 to +1, right? But here, I mean, the way we draw this heat map, we only output the absolute value of the correlation, because after all, we only care about how big this correlation is. If it's close to 1 or close to -1, I mean, basically, it just indicates these two features are on a line, either this line, this direction, or the other direction, like this. I mean, either way around, it's going to have a very bad impact on the model. Okay. So if that's the case, what do we do? Okay, one solution to deal with these highly correlated variables is just remove one. Okay, or if you have more than two, okay, you may want to remove like more than one. Okay, correlated variables. Okay, so this is one way. Okay, we talk about this like in linear regression model chapter. So another option is to put more information into the prior. Okay, so this can be achieved using informative prior if we have useful information. So for weakly informative prior, okay, Andrew Gurman, okay, Andrew Gurman is the author of that red reference book. Okay. And the Stan team. Stan is like if you are writing if you are using R programming language like for Bayesian data analysis, then Stan is pretty much a standard package for you to use. I mean, it's just like if you use Python, I mean, and the PyMC3 is your tool. Okay, something similar to that. Okay, so the Andrew Gurman, the Stan team, okay, they recommend, okay, this one, okay, scaling all non-binary variables to have a mean of 0, and then use this student t distribution of like mean 0 and the v and the SD. Okay, so SD is like chosen in order to weakly inform us about the expected value for the scale. So normal, I mean, as for like this normality variable, okay, v indicate the normality variable. Remember when v is like close to, a large number, this student t is going to be close to a normal distribution. Okay, so this v is suggested to be around 3 to 7. So this prior is saying that in general we expect the coefficient to be small, but we use fat tails. Okay, so in case if there's like occasional outliers. Okay, I mean that's what we meant. Okay, so as we saw like in the previous chapters. Okay, using student t distribution leads to a more robust model than using a Gaussian distribution. Okay, so. Yeah, I think like we probably originally I hope to talk about more things. I mean, but no, it looks like we can only talk about this unbalanced class. Okay, so the iris data set is completely balanced in the sense that each species counts with like 50 instances, right? So it is completely balanced. Okay, but a lot of time, okay. If you you have like unbalanced data. For example, like you get a lot of samples from one class, but not so many from the other class. Okay, so this is something to thank Ronald Fisher for. Okay, because Ronald Fisher is the one who collect like this like iris data set. Okay, and Ronald Fisher happened to be the one who promote the use of p-values, okay, which obviously is not what Bayesian data analysis people likes, okay. Unlike his dedication to popularize the use of p-value, but anyway, okay, you get the idea, okay. So on the contrary, many data sets, okay, consist of unbalanced data, as I said, okay. So there are many more data points from one class than from another, okay. So if this is the case, logistic regression can run into trouble. Okay, I mean, what trouble it is? Okay, it's like the boundary cannot be determined as accurately as when the data set is more balanced. Okay, let's look at an example. Okay, so let's still use the iris data set, but now let's intentionally remove some data points from the Setosa class. Okay, so here, okay, we still use like two classes, Setosa and Vescaler, okay. But now, if you look at here, okay, we, we try to get the entries after the 45. Okay, after the 45. So in other words, okay, because the first 50 is setosa, okay, and then the next 50 is the base color. So we try to remove the first 45. So it means what? It means we only keep 5 entries for the setosa, and the other 50 for the base color remains, in the data in there. Okay. So then, okay, we basically do exactly the same thing. Okay, the other part remains the same. I mean, we already talk about how to do this. So I will hand wave the other part. But what we are going to end up with, okay, I mean, we are still use this one. Okay, if you output the result. I mean, let's compare this one with the with this one. 2 things you can identify. First, if you look at the middle line, this middle line, okay, in the balanced data set case, it's more in the middle, right? It's more in the middle. But in the unbalanced one, you can see that, okay, instead of keeping this black line in the middle, it's actually closer to the class with fewer samples, right? Okay, this is the first thing. The second thing, I mean, obviously, this one, okay, we get a much wider 94% HPD, right? Okay, for the boundary. Okay, for the boundary. So for the first one, it's obvious. Okay, so and there's no other way to explain that. I mean, so that's why we say if the data set is not balanced, okay, this boundary decision may have some issue. Okay, may have some issue, and for the second issue, for the second problem, this 94% HPD is going to be wider. Some people may argue, wait a moment, we already have now we have a fewer data point, right? We have fewer data point. Originally we have 50 for one class, 50 for another class. So totally we have 100 data point, right? And now we have 55, right? So almost half of data point. So since you have fewer data set, okay, fewer data point in the data set, okay, it's nature for your posterior, okay, 94%, okay, HPD to be wider, right? I mean, if you still remember the basic principle of Bayesian data analysis, I mean, this is nature. Some people will argue, okay, this second issue, okay, that HPD is wider, okay, it may not contribute because it may not be because the data set is unbalanced. It's because you have fewer data points in your data set. Okay, this explanation is also valid. I'm not saying this is not correct. So there's an exercise, okay, that you can use. I mean, you can check out that exercise to see that exercise is pretty much trying to tell you okay, we have roughly, because it's 55, right? So roughly let's have the same amount of data, about 50, 55, but now it's even. And let's see how wide. That's 94% PDF is. You can compare with this one and see like, if this is caused by unbalanced data set or not. Okay, and by the way, this is the question that, one of the questions in homework 4. Okay, so just want you to be aware. Okay, I leave this in homework 4 for you guys. You can try to do it like yourself. Okay, all the codes are there. Okay, so you can generate like the figure very easily. Okay. So, okay. So how do we deal? How do we make sure this problem gets resolved? Actually, it's not that easy. Okay. The obvious solution is to get a data set with roughly the same data points for each class. Okay. If you are the one who collects the data, okay. So this can be important to have in mind if you are collecting or generating the data. If you are the one who is in charge of the data collection, data generation, yes, don't give yourself a trouble, right? Just generate like this data set by yourself, okay? So this is, so that you don't run into such a problem. But, okay, if you have no control over the data set, like a lot of time, you get the data set from somewhere else. So this data set is really not controlled by you, okay? So you should be careful when interpreting the result for unbalanced data. Remember, if it's unbalanced, that boundary will look closer to the minority class. Okay, so this is like something you need to keep in mind. Okay, check the uncertainty of the model and run some posterior predictive checks, and to see whether the results are really useful. Okay, because sometimes like when the result is too biased, it may not be that useful. Okay, so no, if that's the case, like another option will be to input more prior information. You can encode more prior information if available, and run alternative model. You can change the model. For this alternative model, again, like a model comparison chapter may come in handy. Okay, hopefully, like we will have time to talk a little bit about that. So we will explain later in these set of slides. Okay, so anyway, so that's for the unbalanced data. Okay. Well, we have only 10 minutes. I'm not sure like how much we can talk about. So I will just try to start this this new topic, but perhaps like we just like have to stop like short of like finishing the first like example. Okay. Anyway, like right now, like we already cover the model that is able to do like a binary classification for us, right? But you may say like a lot of time we have like more than 2 classes, right? We have more than 2 classes. So how do we do? Okay, if you have more than 2 classes, what you can do is that, you can use softmax regression. In the softmax regression, the inverse link function is the softmax function. Okay, you replace the logistic function with a softmax function, which looks like this. So in other words, to obtain the output of the softmax function for the ith element of a vector, mu, okay, we take the exponential of the ith value divided by the sum of all the exponentiated value in the mu vector. So say, if your mu vector if your mu vector is like mu1, mu2, mu3, for example, and you apply this softmax